Another massive wave is taking shape in the weather pattern affecting California, and its scale is already distinguishing it from the systems that battered the state before and after the Christmas season of 2025. After a succession of atmospheric rivers reshaped rivers, hillsides, coastlines, and urban infrastructure, the atmospheric configuration over the western United States has shifted again. Southern California's wild weather is not over, and the next phase introduces a different and potentially more disruptive alignment of forces. Why does this incoming wave carry greater implications than those that came before? How can a region already altered by repeated storms absorb another major disturbance? And why are wind projections now reaching levels that exceed most winter benchmarks? The weeks surrounding Christmas were marked by repeated Pacific-origin atmospheric rivers that delivered long-duration rainfall across large portions of the state. These systems transported moisture across thousands of miles, producing runoff measured not only in inches, but in watershed response, soil saturation, and cumulative stress on flood control infrastructure. Even where rainfall totals appeared moderate by historical standards, the persistence of wet conditions changed the baseline. Slopes that normally shed water efficiently retained moisture. Channels that typically ran low remained elevated. Coastal zones endured repeated episodes of strong surf that accelerated erosion along bluffs and beaches. Those impacts did not reset once the storms passed. They lingered, quietly influencing how the landscape would respond to the next disturbance. Now, as the broader atmospheric pattern evolves, California is facing a wave that is less about sustained rainfall and more about the interaction between residual moisture and extreme wind dynamics. Forecast guidance indicates wind gusts in Southern California may reach up to 85 miles per hour, equivalent to approximately 137 kilometers per hour, particularly in mountain passes, desert slopes, and coastal canyons. These winds are not being driven by Pacific storm flow. Instead, they are associated with a developing Santa Ana wind event, a phenomenon rooted inland rather than offshore. Santa Ana winds arise when high-pressure systems strengthen over the Great Basin and interior deserts of the western United States, including regions of Nevada and Utah. Air flows outward from these high-pressure zones toward lower pressure along the Southern California coast, moving from land toward the Pacific Ocean. As this air descends from elevated desert plateaus through mountain ranges such as the San Gabriels and Transverse Ranges, it compresses, warms, and dries. The result is a powerful offshore wind that accelerates through narrow canyons and passes, often reaching extreme speeds over relatively short distances. This inland-driven wind regime represents a fundamental shift from the Pacific origin systems that dominated earlier in the season. Atmospheric rivers delivered moisture and onshore flow. Santa Ana winds do the opposite, pushing dry air seaward and stripping moisture from vegetation and surface layers. When these winds occur after prolonged rainfall, the risk profile becomes more complex rather than simpler. Wet soils lose cohesion under gust stress. Trees, weakened by saturation, become more susceptible to uprooting. Debris left behind by earlier storms is mobilized, creating secondary hazards for roads, power lines, and drainage systems. Southern California is especially sensitive to this configuration due to its topography. The region's mountain ranges act as accelerators, converting pressure differences into high-velocity wind. Valleys and urban corridors lie directly in the paths of these flows. Wind speeds that may register lower at regional monitoring stations can spike dramatically at localized choke points, producing uneven but severe impacts. At the same time, conditions offshore are far from calm. The Pacific remains unsettled following weeks of storm activity, and wave energy continues to propagate toward the coast. While the Santa Ana winds themselves blow away from the ocean, their interaction with existing swell patterns can produce chaotic marine conditions. Harbours experience irregular surges. Nearshore waters respond unpredictably as offshore winds oppose incoming wave trains, steepening wave faces and increasing the likelihood of hazardous conditions for maritime operations. California's coastline, extending more than 840 miles, or roughly 1,350 kilometers, ensures that these effects are not evenly distributed. Northern sections may still experience residual precipitation from weaker trailing systems, while Southern California contends with wind-driven hazards. Inland deserts face blowing dust and rapid drops in relative humidity. Agricultural regions encounter stress on winter crops and infrastructure exposed to wind abrasion. Transportation networks are particularly vulnerable during such events. High-profile vehicles travelling through passes face elevated rollover risk. Rail corridors contend with wind-driven debris and track obstructions. Aviation operations must manage both mechanical turbulence and abrupt surface wind shifts during takeoff and landing. Power infrastructure, already stressed by prior storms, becomes susceptible to outages as lines sway under sustained gusts. Despite the recurrence of severe weather over recent weeks, each system introduces new variables. Repetition can create a false sense of familiarity, yet this wave differs materially from those that preceded it. The absence of prolonged rainfall does not equate to reduced impact. Instead, the focus shifts toward wind intensity, duration, and interaction with a landscape that has not yet recovered from earlier storms. The timing of this wave further complicates response efforts. Repairs to storm-damaged infrastructure are still underway in many areas. Temporary reinforcements remain exposed. Emergency management resources have been cycling continuously rather than resetting between events. A system that might otherwise be manageable in isolation now arrives amid ongoing recovery operations. Questions naturally arise about why these disturbances continue to arrive in such close succession. Seasonal variability explains part of the pattern, but the persistence observed this winter suggests a broader atmospheric alignment. The jet stream has remained active and favourably positioned to steer systems toward the west coast, while inland pressure patterns periodically strengthen enough to trigger offshore wind events. Small shifts in these large-scale features determine whether California experiences calm intervals or renewed disruption. As this next wave approaches, attention increasingly turns to factors that are not immediately visible on radar or satellite imagery. Beyond rainfall totals and wind speeds lies a subtler condition that has been quietly influencing how each system behaves upon arrival. It is embedded in the background state of the atmosphere and ocean, shaping intensity, duration, and geographic reach in ways that only become obvious after impacts are felt. That underlying condition has already affected previous storms, though its role has not been widely recognized. Now, as inland pressure builds and winds accelerate seaward, its influence becomes harder to ignore. It helps explain why this wave is expected to exert broader and more forceful effects than recent events, even without record-breaking rainfall or unprecedented measurements at first glance. The full implications of that factor and why it elevates this wave above the rest will become clearer as the system unfolds further and its interactions compound across land, air and sea. As the incoming wave advances toward California, its behavior is being shaped by conditions that extend beyond the immediate storm structure. The state is no longer responding to isolated events, but to a sequence of interlinked atmospheric processes that reinforce one another over time. Each system modifies the environment just enough to influence the next, creating a compounding effect that becomes more evident with every passing week. One of the most immediate consequences of this compounding pattern is the strain placed on surface stability. Soil across much of California remains unevenly saturated. In coastal and foothill regions, repeated rainfall earlier in the season penetrated deeply into ground layers that typically dry out between storms. Even without heavy new precipitation, strong offshore winds exert force on trees, slopes and man-made structures that are no longer anchored as firmly as they would be under normal winter conditions. Uprooted trees are not simply a product of rainfall or wind alone, but of timing and accumulation. Urban areas face a different but equally complex set of pressures. Storm drains, culverts and temporary flood barriers installed during earlier atmospheric rivers were designed with water flow in mind, not extreme wind loading. Gusts approaching 85 miles per hour, or approximately 137 kilometers per hour, introduce stress in directions and magnitudes that these systems were never meant to handle. Construction zones, scaffolding and temporary repairs become focal points for secondary damage as unsecured materials are displaced. The power grid reflects this vulnerability clearly. Transmission lines traversing mountain corridors are exposed to both sustained winds and sudden gust spikes as air accelerates through terrain bottlenecks. Poles embedded in softened ground experience increased sway. Even brief interruptions can cascade across interconnected systems, particularly when demand remains elevated due to heating needs in cooler inland regions. Marine conditions continue to evolve in parallel. While Santa Ana winds push air offshore, the ocean responds to energy that was injected days earlier by Pacific storms. Long-period swells, generated far from the coast, arrive regardless of local wind direction. When offshore winds oppose these incoming swells, wave faces steepen, reducing stability and increasing breaking intensity near shore. This interaction does not require additional storms to produce hazardous outcomes. It is a delayed response, one that unfolds quietly until conditions suddenly deteriorate. Harbours and ports experience these effects in subtle ways. Mooring lines are stressed by irregular surges. Vessels pivot unexpectedly as wind and water forces act in opposing directions. Operations that depend on predictability are forced into adjustment even in the absence of headline-grabbing rainfall totals. Inland, the offshore flow carries additional consequences. Relative humidity drops sharply as dry desert air descends toward the coast. Vegetation that benefited briefly from winter rainfall begins to lose moisture rapidly under persistent wind. Fine fuels dry first, followed by heavier materials. While this does not guarantee ignition, it narrows the margin for error considerably. A single failure within an already strained system can produce outsized effects when conditions align. The timing of this wave magnifies all of these factors. Coming on the heels of multiple atmospheric rivers, it arrives when recovery efforts are incomplete and fatigue is evident across systems both physical and administrative. Resources are spread thin. Crews that would normally rotate between events are instead responding continuously, with limited opportunity for reset. Yet the reason this wave is being described as bigger is not confined to any single metric. It is not solely about wind speed or rainfall totals or coastal wave height. The distinction lies in the background state of the Pacific and the atmosphere above it, a condition that has persisted quietly throughout the season. Sea surface temperatures across broad sections of the eastern Pacific have remained elevated relative to long-term averages. This warmth does not always manifest as immediate surface weather, but it alters the energy balance of the systems passing overhead. Storms draw strength more efficiently. Pressure gradients sharpen more readily. Atmospheric features that might otherwise weaken retain coherence longer as they move inland. At the same time, the jet stream has exhibited an unusual steadiness in its alignment. Rather than oscillating north and south in a way that would bring extended calm periods, it has maintained a configuration that favours repeated delivery of energy toward the west coast. Even when individual storms dissipate, the pathway remains open. The reveal, then, is not a single hidden storm or an unseen surge waiting offshore. It is the realization that California is operating within a sustained high-energy regime, one in which land, ocean and atmosphere are temporarily locked into a reinforcing cycle. Each wave, whether wet or dry, builds upon the last. The current event stands out because it draws simultaneously on residual moisture, extreme offshore wind, and an energized ocean state, combining impacts that are often separated by weeks or months. This explains why projections indicate broader effects even without unprecedented numbers appearing in isolation. It also explains why familiar warning thresholds are being crossed more frequently. The environment itself has shifted, and within that shift, systems behave differently. As this wave unfolds, its impacts will not be confined to a single day or location. Some effects will appear immediately, such as wind damage and power disruptions. Others will emerge later, as weakened slopes fail or coastal erosion accelerates under delayed wave energy. The full scope will only become apparent over time, as the compounded consequences of the season reveal themselves across California's varied landscapes. What is clear now is that this wave represents more than another entry in a long list of winter disturbances. It reflects a moment when multiple processes converge, testing the limits of infrastructure, preparedness, and environmental resilience all at once. How California responds to this phase will shape not only the immediate outcome, but the state's readiness for whatever follows in the weeks ahead. If you found this breakdown valuable, like the video, share it with others who need to understand what's coming, subscribe for continued coverage, and tap that hype icon to help this video reach a wider audience.